we have our next speaker already here with us. We've seen him before. Michael is a known face to us. We've known him here in the SDRA right from the beginning. No, we've known him. He is my partner in the SDRA. We have set up the SDRA together. So, well, he's been here from the right from the beginning. Michael is a professor at the University of Applied Sciences in Bremen, Hochschule Bremen, and he's an electrical engineering professor, and he's a radio amateur for so many years. And Michael, you've never told me how long you have had your license, but a long time.
I have to look on the license.
A long time for sure, a very long time for sure.
Yes.
And Michael is very experienced in everything that's related to signals and spikes, particularly from high voltages and all those funny things. And yeah, and of course these spikes in signals and wanted and unwanted spikes in signals is obviously a very interesting topic, particularly when they're generated everywhere in power supplies and all kinds of funny sources. And this is why Michael got very interested in analyzing and investigating how noise develops, and where noise comes from, not just particularly from one spot, but in a very broad distribution across the country. And he's one of the core contributors of the ENAMS project, and we're going to hear a very interesting talk from him now. So Michael, as before, we've pre-recorded this video. I'm handing over the control to our video team, and we're going to talk about the questions later. The audience is welcome to post the questions in the chat. Sebastian, please go ahead.
Thank you, Marcus, for the introduction. I want to talk today a little bit about the noise measurement system for man-made noise, ENAMS. I was talking several times about that, and now the focus is laid on signal processing in this system. What is ENAMS? This is an idea of the EMI unit. The head of the EMI unit at the German Amateur Radio Club, DARC, is Klaus Eichel, call sign Delta Lima 6 Sierra Echo Sierra. And his idea was to have an independent standalone system in the range from 50 kilohertz to 31 megahertz, measuring several times per hour. The measurement results must be comparable to results of standard measurement procedures. I think well known are the EN 55000 and the ITU regulations. The system should consist of a centralized server for administration and data collection, as well as for control and backup, but it should have decentralized independent measurement systems. 50 locations spread over Germany will measure according to the ITU regulations paper 372 categories, which I explain later. Stable parameters over the next 5 years are expected or should be realized. If you want to have further information, have a look on enams.darc.de. Why do we need it? International treaties bind nations to use spectrum according to the ITU regulations. Well, the EMI certification measurements are emission of individual devices. And from 0 to 30 megahertz, there is only measured the conducted line emission measurements, but not radiated noise, because the laboratory size is less than the wavelengths of low frequencies. Increasing number of power electronic devices without CE certification are imported into Germany and other European countries. fast switching power electronics in solar converters and optimizers for solar systems using with the fast switching systems make a big noise in the shortwave range because of the long lines they are connected. There could be a solution to collect verified arguments against radiated radio noise below 30 megahertz. And this is the idea of ENAMS. Noise monitor systems in ham radio activities known to me are the ARRL noise measurement campaign. At TAPA, there's a working group which makes the development of Tangerine SDR. In IARU Region 1, there's a discussion of the EMI managers, and several national initiatives in Europe, in Great Britain, Netherlands, and Switzerland are known to me. This is an open but not a completed list. Well, we get some help from the ITU regulations and the recommendations are in paper 372 in the latest version from August 2019. The title is Radio Noise, and it explains how to measure it. I will show you one of the figures from these recommendations. These recommendations show frequency spectrum from left to right up to 300 megahertz. Okay, we focus on the 30 megahertz and below. And you see 4 lines, A, B, C, D named, and these lines are the noise figure for this actual frequency in surrounding or an environment, industrial, residential, rural, quite rural, and galactic is the E. It's a very low line, dotted line. Well, this is referred to a special defined antenna, or you could say a field sensor. Recommendations make up a question: what is the real noise figure for my location? I show you some measurement which I made on Sunday at 11 GMT in Bremen. And you see 2 lines, a blue and a red line. The blue line is an average, not the RMS value, an average spectrum of some measurements, and I would say it's a momentary amplitude. You see the frequency range from 0 to 62 megahertz on the right hand side of the graphic, and well, you see the red line. The red line is the peak measurement, only pushed up by one impulse within a measurement time of 20 seconds. The 20 seconds are just a selected time. We can have longer time for measurement, but then maybe we get some more pulses. This is only one impulse. I should explain here that the different amplitude is 15 decibel between the momentary status and the peak value where it crosses. I suspect this is power line carrier, since power line carrier in waiting position does no transmission to the network, and only one pulse of one packet is every few seconds to show and to ask the opposite station if they is still active. What do we expect under the results of the RF EMI monitor? There are some questions what I want to explain. What are the superimposed results of many electrical systems? What noise level could be found in different ITU regulation categories? What frequency range is concerned? What is the longer-term development of man-made noise over months and years? With 15 stations in Germany, a geographical distributed heat map of noise and the dependency over time will be expected in the future. There are some more standards and recommendations. Mainly is the CISPR 1611 from 2015 for measurement instruments, and the other of the CISPR 16. And from the ITU, they are open. The spectrum management 2055, 2125, and 2155. There are a lot of other standards which could be mentioned here, but I think that's enough for now. Well, a conventional measurement from CISPR 1611 suggests to have a sequential tuned receiver. One frequency lasts for 1 second. And when you have an example, you look here, it is 841 kilohertz, 1 second, and then it's going up to 850 kilohertz, 1 second measurement time, and so on. And you see the time is increasing. When you want to measure from 65 kilohertz to 30 megahertz, one measurement needs about 3,326 seconds. This means it's about 56 minutes with a 9 kilohertz filter. With this procedure, a new measurement repeated every 10 minutes is not possible. So our measurement system should have another concept. And well, I should explain the ITU P372 noise figure. It refers to a quarter wavelength monopole antenna as a sensor. This means if you are measuring on 100 kilohertz, you have to have a quarter wavelength monopole antenna. Quite a good idea, but not to realize in amateur equipment. ENAMS uses an active antenna 1 meter's length, 1 meter high over a radial network on ground. It is very important to put that on ground, not on the roof of a garage or anything else. The ENAMS system is, well, I apologize for the German picture, but I will explain in short. On the left side, we see the receivers, and the receiver consists of a Red Pitaya, this small red picture, and the measurement data are put server. The server is operating the measurement data and collect them, put them in an SQL database, and produces some evaluation of the data and made a web server available to show the results. I will explain a little bit of the results later. The measurement procedure of ENAMS goes in the following steps. The Red Pitaya has a 2-channel 14-bit analog digital converter with 125 megahertz sample rate and a Linux OS. It takes 1 second sample to the RAM disk by using an HDSDR FPGA module. This is common used for GNU Radio. Pavel Demin, who is a scientist at University of Leuven in Belgium, made this FPGA module and the other software for it. And we used it here with a Python algorithm. We expect 1 second with a sample rate of 1.25 megahertz in the broadband, and we select one of the medium frequency 1.2 megahertz, and we go up later. This 1 second is sampled to the RAM disk. We calculate the power spectrum density with 300 hertz binbus, store this power spectrum density, and take 29 steps. Each is 1 point and a little megahertz wide, and step up, step up, step up. This takes 29 steps to get the full range which we want to measure. We add a peak measurement for pulse amplitude with 9 kHz resolution. Put the results to a collecting central database station. This means 110,000 bins per measurement. The measurement itself takes about 5 minutes 30 seconds. The repeat measurement could be started by cron or system D every 10 to 15 minutes. We calculate more results on the server. This means make some calculations, mean, RMS, peak hold, calculate and show results for different bandwidths, even for 300 Hertz for telegraphists or for SSB or the ITU recommendation with 9 kHz. This is important to have a comparison to people who wants to see what the results at their own receiver will bring on the S meter. The server is for further evaluation and comparison. The estimation of spectral distribution with pulsed sine wave, well, an example is electronic power supply or converter are producing pulsed sine waves. Calculate the power spectrum density is done using the Welch algorithm. Split total 1.25 megasamples into overlapping windows of 4,096 samples. An overlap of 50% is used. This results into 612 individual time-dependent spectra with binwidth of 305 Hertz. Then apply over time an algorithm for root mean square, for peak, or everything else what is needed. We selected RMS and peak. The pulse length of 1.6 milliseconds results into full peak power with this measurement method. Let me show an example. Here you see a time scale of 10 seconds. Sample rate is 10 kilohertz per second. This means 10 seconds is 100,000 samples. And we have a pulse with 1234 hertz for a time of 200 milliseconds. This means it's 2% of the total time window. And you see in the left hand side, there is a big noise level up to 7.5 volt. Peak to peak is 15 volt. And where there is the small sine wave pulse, you see a little increase of the noise level, but it's not very good noticed. Look at 7 seconds. You see some equivalent large amplitudes and noise, but there's no reason for it. It's just distributed noise. And I made a zoom into it from 4.8 seconds to 5 seconds. You see the 200 milliseconds of the pulse in the right picture. The results of spectrum estimations, the window with 1,024 samples here per segment it's about 1 millisecond. The Henning window for Welch transformation is used, 50% overlap, and the calculated PSD is shown in the picture. When you calculate the maximum from the 197 windows obtained from this example, you see the table of the amplitudes, and you see what is the reference to the mean. You see the medium is a quarter of the mean. The peak is 50 times of the mean, and the RMS is 6 times of the mean. So when we measure the peak and the RMS, we will find out right time. Okay, Some results based on ITU are paper 372. RMS of the ITU noise figure is shown here. We see a day, the 20th of January, the 14th of January 2020 at the station number 4. It's an RMS, and we see the noise figure. The noise figure is the color. We see at the low frequencies some more amplitude, and the upper frequencies are near the noise figure of 30 decibel. When we take a line at 7 o'clock and make a two-dimensional picture of it, we see this. It refers to the ITU lines, industrial and residential and rural. You can see that the measurement is above industrial and sometimes between residential and industrial at the higher frequencies above 3 or 5 megahertz. We transformed and based it on rural, and then it could be easier interpreted from not an expert. I think this is a good idea to have a rural-based system, and here we put in the rural line at 0 decibel, and so we have a deviation against rural. You see, there are some decreasing amplitudes at the hem bands. The hem bands at 14 megahertz, at 18, at 21, and at 12 meter near 25 megahertz. When we display this for the whole day, we have a waterfall based on rural, and you see very dark lines at 14 megahertz, at 10 megahertz, 25 megahertz. It's quite impressive to see what is the reduced power of noise. On the other hand, you see from 16 megahertz to nearly 20 megahertz, you see a lot of noise in it. We can use this noise power in hem bands and in other frequencies and calculate the noise power as deviation to rural and showing this dots over the time. So we transformed the three-dimensional picture back to a two-dimensional picture, and you see what is the difference in time over the time of the day. What is the momentary status of the ENAMS project? An increasing number of 15 stations are in operation. Official measurements since end of 2019 are done. The team is producing more stations and bring them into operation. New measurement procedures are now tested. The evaluation of measurements is redefined all the time in the past. And the SQL database is introduced. The decentralized station, we use a GNU database. It's one of the oldest databases in the Unix world. So let me conclude. An environmental EMI could be measured with SDR. ENAMS is in operation. Comparison with the radio noise regulation is a must for external argumentation. Noise figure depends on time and frequency. Thank you very much for your attention. I look forward for questions or comments.
Okay. Okay, hello, back again. So we're in the right now already together with Bart Sommers here, but let me first
Hi.
let me first say thank you to my colleague Michael Hartje. Michael, you have responded already in the chat to the questions that have come in from the audience. And, you know, because of this LTE tower that has gone down and the network outage, we need to catch up a little. So I would also suggest here, if, dear audience, if you have questions, please write them in the chat, and Michael is going to respond to these questions in a written form, and you can get his response from there.